But otherwise, let's get started. The first talk will be on differential privacy, and Tetsuya Sato will give the talk. Please.
Okay, thank you for introduction. So I'd like to talk about formalization of differential privacy in Isabelle HOL. Okay. So in this talk, I first explain what is differential privacy and its intuition and definition and the results that we formalized. Next, we explain the formalization of differential privacy in Isabelle HOL. So we explain the formal definition and formalization of basic properties of differential privacy. Then we formalize Laplace mechanism. Finally, we will see the formalization of report noisy max mechanism. Okay, let's move on to the introduction of differential privacy. We first consider a scenario of privacy leakage. Imagine an apartment. 999 people live here, and the apartment has the average income query. And then step one, the average income is $5,000. So in the first step. Step two, now Bill, the 1,000th person joined the apartment. Then the average income changes to $5,000 plus 1. Step 3, then in this case, the average income query shows only just the average of income. However, it leaks the Bill's private income. We can calculate $6,000. So it is a very cheap scenario of privacy leakage. I want to say that the average income does not show the Bill's income itself, but using the background knowledge, so privacy can be leaked. To prevent such privacy leakage, we can add noise to the query of average income. So in such noisy query, for example, the average shows as follows. In the case of 999 people, the query shows the $5,000 plus 2. Here, the noise is plus 2. And in the case of 1,000 people, the last person is Bill. The average shows the 5,000 plus 1. Here, the noise is plus minus 0. So importantly, the amount of noise is basically small. However, it is statistically harder to determine the Bill's income. So it is an intuition of differential privacy. Actually, to realize the differential privacy, we need to discuss the specification of the average income query, and we need to discuss the shape of noise. Okay, let's move on to the definition of differential privacy. So in the definition of differential privacy, we consider a randomized query. A randomized query M from X to Y. Here, X is the domain of data set. Y is the domain of output. The randomized mechanism M is epsilon delta differentially private for any adjacent data sets, D and D prime. Here, the adjacency means that the two data sets, D and D prime, differs only in one record. So for adjacent data set, D and D prime, the distributions MD and MD prime of output of the mechanism M satisfy this inequality condition. So this condition seems rather complicated, but the intuition is very simple. The ratio of probability between MD and MD prime is bounded by e to d epsilon, except in the probability delta. So in short, the parameter epsilon stands for the ratio of probability between MD and MD prime, and delta is the probability of error. Importantly, if epsilon and delta are small, the two distributions, MD and MD prime, are hard to distinguish. In particular, if both epsilon and delta are 0, the distributions MD and MD prime are the same. So I here remark on the adjacency of data set. Differential privacy is a definition to hide the small change of data sets. So it depends on the structure and the adjacency of data set. In this talk and in my paper, we consider data sets and adjacency as follows. First, each data set D is a finite list of natural numbers with length n. Here, each record D of I shows the number of data in class I, and the data set D itself can be understood as a histogram. Next, the adjacency of data set is defined by the L1 metric. D and D prime are adjacent if and only if L1 metric between D and D prime is bounded by 1. In this case, D and D prime differs only in one record. Okay. Next, to realize differential privacy, we need to add noise, I said. So here is a typical mechanism of noise addition of Laplace mechanism. Sorry. It is a typical mechanism of noise addition. So a noise adding mechanism of Laplace distribution. So LAP-B is so for given scale parameter B, we can consider the noise adding mechanism LAP-B. And then for given value x, LAP-Bx is a Laplace distribution of mean x with scale B. So definition of Laplace, okay. So here is density function and the shape of Laplace distributions. And the Laplace distribution has a nice property for differential privacy. So if the given values x and y differs only, difference between x and y is bounded by R, then the ratio between the Laplace of x and Laplace of y is bounded by e to the R over b. So in short, these two distributions, the ratio of two distributions are bounded by some constant everywhere. Okay. Next, Laplace mechanism. It is a typical mechanism for differential privacy. So it is a mechanism adding Laplace noise to each element of output of the process F. Here, we consider a process to anonymize F. F accepts the data set and returns the m values, tuple of m values. And the Laplace mechanism adds noise to each x of I, and then produce the noisy tuple. So we can discuss the differential privacy of Laplace mechanism. We use the sensitivity of the process F. Sensitivity is defined by the least upper bound of the difference between FD1 and FD2, where D1 and D2 are adjacent data sets. So using this adjacency, the differential privacy of Laplace mechanism is delta F over B, 0, differentially private. So it is a typical example of differential privacy. Here, report noisy max mechanism is an application of Laplace mechanism, but so it contains a non-trivial result. Okay, first, report-knowledge max returns the index of maximum value in a Laplace mechanism for the counting query. So first, we consider a Laplace mechanism for the counting query. So counting query means that each counting query counts the number of data of some classes in a data set D. And then each counting query has sensitivity 1. And then, so then we consider a tuple of M counting queries, and then this part has sensitivity M. So we also consider the scale parameter 1 over epsilon. So, and then we apply the argmax operation after that. So naively, the differential privacy of report-knowledge max mechanism can be evaluated as a M epsilon 0 differentially private. However, it is actually epsilon 0 differentially private regardless of M, the number of counting queries. The proof is not so simple. It is done by evaluating the distribution of report-knowledge max mechanism directly, and by applying the statistic properties of argmax operations and counting queries. Okay, so we briefly see the result what we formalized. In this work, we formalize differential privacy. We give a differential privacy library in the continuous setting and in a proof assistant Isabelle HOL. So the motivation to the continuous model is as follows. First, a continuous model is more general than the discrete model. Second, some studies of differential privacy consider ideal mechanisms written in the continuous setting. So for example, in the study of floating point implementation of Laplace mechanism by Mironov, so in the paper, so snapping mechanism, which is a floating point version of Laplace mechanism. So in the proof of its differential privacy, we need ideal version of Laplace mechanism. Secondly, so in the study of F differential privacy, which is a very latest extension of differential privacy, so to prove the composability of this, we need a continuous model, even if we consider only the discrete mechanisms. Okay, I remark that formal verification of differential privacy in the discrete setting is already implemented in several proof assistants. In Coq, for example, in Coq, the CPP' library contains a discrete version of differential privacy and the implementation of relational HOL logic reasoning about differential privacy, and the discrete version of Gaussian mechanism. In DIN, so in the Sato, it is a very recent formalization of differential privacy. So in the Sato library, there is a discrete version of differential privacy and a discrete version of Rayleigh differential privacy. It is a relaxation of differential privacy. And also it contains a discrete Laplace and discrete Gaussian mechanism. And interestingly, it also contains a causal generation. So coordination to the executable code. Then, in this work, we formalize differential privacy in the continuous setting. I focus on the continuous setting and in the proof assistant Isabelle HOL. Our formalization consists of the 3 parts. First is the mathematical foundations. So there are many preliminary theorems, and so measurable space theory of finite list, and the Laplace distribution itself. And the second part consists of the main library for differential privacy. So we implemented the statistical divergence for differential privacy and formalization of differential privacy and the basic properties of differential privacy. And then we formalize the Laplace mechanism. The last part consists of the formalization of report origin max mechanism. Okay, so in our formalization, we use probability theory library in Isabelle HOL. It is a standard library of Isabelle HOL. So the standard library contains the measure type and the monad for probability, which is called as a Gilly monad, and Radon-Nikodym derivative, which is used for the composition theorem of differential privacy, and the Lebesgue measure. So in our formalization, we use various constructions in the standard library, in particular, a probability theory library. Okay. Then we finally check the Isabelle HOL formalization of differential privacy. So we record the we record the definition of differential privacy. A randomized mechanism M is epsilon delta differentially private if for any adjacent data set and D and D prime, then the distribution MD and MD prime satisfy this condition. So to formalize this definition, we formalize this condition first. And then we formalize this definition as this definition. We here remark that in our formalization, we consider abstract data set and adjacency. So usually, adjacency relation is assumed to be the symmetric. But in our formalization, the symmetry is dropped. Because in the proof of report origin max mechanism, we use asymmetric adjacency relation in the proof. So in our formal definition of differential privacy, we have two inequality conditions in both sides. Okay. Then we formalize the several basic properties of differential privacy. First, differential privacy is stable for post-processing. Consider a mechanism M. It is epsilon delta differentially private. Then, for any post-process F, the composition of the private mechanism F, the private mechanism M, and the post-process F is still epsilon delta differentially private. So here is our formalization of stability for post-processing. And actually, we provide the formal proof in Isabelle HOL. So it is very simple. Second, differential privacy also has the composition theorem. It is a main feature of differential privacy. So intuitively, we compose the private mechanism M and N, epsilon 1 delta 1 differentially private, and epsilon 2 delta 2 differentially private. We compose M and N, we obtain the epsilon 1, epsilon 2, delta 1, delta 2 differentially private mechanism. So here, M accepts only the data set. However, N accepts the data set and accepts the output of M. So to describe this condition, we need to assume that for any y, which is output of M, so it satisfies differentially private with respect to the parameter x. So in the Similarly, we provide the Isabelle Hall proposition, and we give the formal proof. And then we formalize Laplace distribution and Laplace noise. And we first Laplace distribution. So the formalization is inspired from the formalization of normal distribution in the standard library. So, and we consider the density function and the cumulative distribution function, and we prove these correctness, and then we formalize the Laplace noise mechanism, formalization of Laplace noise. So it is a Laplace distribution centered at a given value x. And then we formalize, we prove that so this construction satisfies the desired property. Next, we consider the tuple of Laplace noise, bundles of M Laplace noise. So in the formalization of this construction, we use list instead of tuple for simplicity of formalization. Here, the construction wrap this list, add noise to the each entry in the list of real numbers, and then returns the noisy list. So we define this construction recursively, and then we show the correspondence to the desired definition. Then we formalize Laplace mechanism. Okay. So to give the Laplace mechanism, we need to define the sensitivity of the F to anonymize. And then the definition is so rather straightforward with respect to the its mathematical definition. And then we define the Laplace mechanism using the previous construction of Laplace noise. And then we prove the differential privacy. So in the proof, we use the composition theorem of differential privacy and the nice property of the Laplace noise for the differential privacy. So we here remark the formalization of data sets. So we first we use list instead of tuples, and so to define the adjacency of data set, we introduce the L1 metric between the list. So in the construction of such metric, we use the locale metric space in the standard library of Isabelle Hall. Then we finally formalize the report noisy max mechanism. The formal definition is rather simple. So we formalize this part and the counting query, and first, and then we put the construction of Laplace mechanism. So then we show the differential privacy of the report noisy max mechanism. So in the paper, we provide the naive evaluation of differential privacy and the final evaluation of differential privacy. So the proof of the final evaluation is very complex. For detail, see the proceedings. Okay, we conclude my talk. So in this work, we develop Isabelle Hall library for differential privacy in the continuous setting in Isabelle Hall. So in this talk, we omit almost all the detail. For the detail, check the paper. And so we have formalized the differential privacy of the report noisy max in the continuous setting and related to basic results. And here is my future work. So ultimately, I'd like to formalize the stochastic gradient descent mechanism for differential privacy. So in the construction of gradient, for the differential privacy of this mechanism, we need to formalize the relaxations of differential privacy, in particular Renyi differential privacy. For the technical basis of the Renyi differential privacy, we want to formalize the F divergence. Also, so I also want more examples that based on the continuous model, for example, continuous version of exponential mechanism. Thank you for your attention.
Thank you very much. All right, we have some time for some questions. Anyone? Yes.
So thanks for the talk. You mentioned that one of these proofs were complex. Is this complexity due to the complexity in the paper proof, or is just the automation in Isabelle not working well with dealing with probabilities, etc.?
It is a kind of complexity of paper proof. So, so a student is proving the report noise max in the discrete setting. Even in the discrete setting, the proof costs over the 1,000 lines.
Thank you.
So, and my proof in the continuous setting costs about 1,500 lines. So, we need to convert the program of the report noise max to evaluate the distribution of the report noise max so correctly.
Thanks. Then there's another question here.
Thanks for the talk. Have you considered building some kind of program logic on top of this definition of differential privacy?
Sorry, I couldn't get, keep your voice up.
Yes. Have you considered building a program logic on top of this in the style of APR-HL or?
APR-HL?
Yes.
So, sorry, please repeat the question. Sorry.
Have you considered, or would it be possible to build and formalize
okay, it is possible.
program
Okay,
logic?
I see. Actually, our proof contains central data. So divergence for DP is a central data of the program logic for the quantitative difference of computational effect. And so APR-HL is generated from this data and several results on the specific results. So I believe that we can implement the APR-HL, but I choose the direct one. So, but I already have the central data, and if we want, we use from this, and we can give the relation lifting, and then we formalize the APR-HL.
Thank you very much. Other questions?
Do you think your proof can be formalized in ROC or Lean as well?
Huh?
Do you think your proof can be formalized, the continuous part, in ROC, like following the work of Bart and other?
Sorry.
Do you think your proof can be formalized in ROC or Lean as well?
Lean. Yes, I think so. I think so. So I think so. Yeah. I think both D and Coq already contains the technical background of our formalization. So in theory, in Coq and Lean, we can formalize the so we can formalize as our paper, and but I choose Isabelle HOL because so Isabelle HOL contains so many useful but subtle results on the probability theory, and also Isabelle contains a powerful tool of sledgehammer. So I use so frequently of the I use the sledgehammer so frequently. So yeah. But we can formalize. Yeah. So I believe that they can be translated to the lean. Yeah, I think.
All right. Thank you very much. I think we should thank the speaker again.